Let's start a full controller design for this given plant. Now again, we are going to skip over the modeling step. That would usually be done first so that we know what is the transfer function for our plant. So we'll presume that we did that and we got that our transfer function for this first order plant is 1 over s plus 2. So we want to design a controller so that the output of our plant is going to have a desired response and so that it's going to go to some constant value. So for this example, we want our controller to 1, stabilize the output of our system. We want the steady state error go to 0. We want the maximum overshoot to be 18%, and we want the rise time to be 0.75 seconds. And our input into the system, which will be the desired response of the system, is going to be just a unit step function. So because we want this desired output response for our plant, we need to build a controller around this. We need a closed loop system so that we can get the response that we're interested in. So the first thing we want to look at is which controller or family of controller do we even want to use that's going to accomplish the first thing, drive the steady state error to 0, which is drive the output to a constant value of 1. So let's see some different choices that we could make when just choosing the general controller. Right, so again, it has to drive the error to 0 before we even worry about the other requirements, the overshoot and the rise time. So it's possible that multiple controller designs that we have covered in this course or other ones that we haven't covered could do this first step. What we want to do is check each of them analytically. Will they, in theory, be able to drive the error to 0? And we're going to try a proportional controller, a proportional derivative controller, and our new PID controller for this. But again, there might be other ones that could work as well. So if one or maybe multiple groups of controllers work, then we want to take it to the next step, where then we can worry about the gains and actually implementing this controller and testing it for its validation. But if a controller is not going to drive the steady state error to 0, there's no reason to go further with it. Let's look first at the simplest controller, just a proportional controller. So the transfer function for a proportional controller is just, I will designate it as Kp. It's just going to be some constant times the error, so the controller is just the Kp that we select. The plant transfer function that we were given is this 1 over s plus 2. And the closed loop transfer function, and this is going to be true for all of the systems we're going to look at. Because we're assuming we have a perfect sensor, a perfect actuator, they're just 1. As we've seen from all the previous examples in this unit, the closed loop transfer function will be our controller transfer function times the plant over 1 plus the controller transfer function times the plant. So the algebra, I did all of the algebra for these examples in the associated Mathematica notebook file. So I'm just including the results here, but this is all algebraically. If I multiply these two transfer functions together and then put it in a form with descending powers of s, I get for the P controller that the closed loop transfer function is Kp over s plus quantity 2 plus Kp. That's my constant term. Now that I have the closed loop transfer function, I want to see what happens to y of t as t goes to infinity. That will let me see the steady state value of my output y. So I can use final value theorem for this. So on the left hand side I have the steady state value of y of t. So I'm finding that by the limit as t goes to infinity of y of t. That's what y steady state is. So I know from final value theorem that that's the same as the limit as s goes to 0 of s times y of s. Well, using the closed loop transfer function, again multiplying through by r of s, I know that y of s is r of s times GCL. So that's what I have here. The r of s, because it's a step function, is going to be r of s when I'm in the frequency domain, and I multiply that by GCL. All right, so as we've seen before with previous examples, the s and the 1 over s are going to cancel out. I'll be left with this r times Kp over 2 plus Kp. That's going to be the steady state value in the time domain of my output. So what we are testing here first is, does the steady state error go to 0, which is to say, does the steady state value of my output go to really the amplitude of my step function? So here we see no, it does not, because it depends on the value of Kp, depends on the gain I choose in my controller. This is another example like we saw in the earlier lecture, where if I choose a very high value of Kp, then it's going to asymptotically approach R, but it's not going to identically approach R. And a problem with this is going to be, one, I can never get to the desired steady state value, and second, I can get close to it, but it's going to come at the expense of a very high gain and a very high input effort needed on this controller. So we're going to say that the proportional controller for this plant does not work. We do not identically get our steady state value to be equal to R, the amplitude of that input. So we are not going to want to proceed with a P controller here. We're going to want to move on and try a different controller. Right, so maybe a PD controller is going to work. The general form we're going to use is the KDS plus KP, as we saw a couple lectures ago. The plant transfer function has not changed. That's still 1 over s plus 2. And the closed loop transfer function is still going to be found exactly the same way, but we have a different GC than we had for the P controller. Again, I did the algebra in Mathematica, and I have it shown here in descending powers of s. Right, so I have a KDS plus KP in the numerator, and then 1 plus KD is my s term, a 2 plus KP is my constant term in the denominator. So same idea as the previous P controller test. I want to know what happens to my steady state value. I want to know what happens to YSS, or y of t, as t goes to infinity. So again, I'm going to use the final value theorem here, so I can see what happens to s times y of s as s goes to 0. Now, again, we do want to make sure the denominator, or the poles of sy of s are all in the left half plane to ensure that we can use final value theorem. So I am making that assumption at the moment here, but we do want to check that when we actually implement our controller. But we see that either way, when I go through the algebra here and I assess s at 0, I get that the steady state value is, again, r times kp over 2 plus kp. So once again, this controller will not work because it does not drive the error to 0, which is to say that the steady state value does not always go to R. It's dependent on the proportional gain that we choose. So a PD controller for this plant also does not work. So we're not going to proceed to do any more design work with it. Right, so we can move on. Let's try the new PID controller and see if it will even work. Right, so I'm going to implement it using these 3 gains. So an S, a constant, and a 1 over S. So KD, KP, KI I'm going to choose for this controller. The plant, again, is exactly the same as it's been. And the closed loop is going to be calculated the same way it was in the previous 2 steps. So going through the algebra, this is what I get for my closed loop transfer function. So let's see what happens to the output, the steady state value of the output. So again, I want to use final value theorem here, and now when I let s go to 0, I am going to get just r. And if we see what happens, the s squared term, that goes away, the s term goes away. The fractional part, I'm left with a ki over ki, which goes to 1. So what I'm left with is r. So given enough time, the steady state value of the output goes to r, which is exactly what we need to have happen. So at least the first test, this controller passes. It will eventually make the error go to 0, or the steady state output go to R. So the PID controller will work to at least do that. So we're going to take this on to the next step in going through, well, what gains should we choose so that we get the behavior that we're actually interested in? But at least we know that given enough time, it does drive the error to 0. If we look at the poles of sy of s, once again, we have to make sure that the poles of sy of s are all in the left half plane. It is possible that we could choose values of kd, kp, and ki, which would make those poles not all in the left half plane and make our controller unstable. That's a distinct possibility. So if we pick the 3 gains such that all of the poles are in the left half plane, then we can say yes, the steady state error will go to 0. So it is not true for any ki, kp, kd combination that we choose.